All right, so I've got my slides fixed. So here we go. All right, so now that I got them fixed, we can take a look at it. Hopefully your PDF looks like this. So first thing we're looking at is electric potential difference, and that should be in energy, okay? So electric potential difference, and we are talking about energy in this particular topic. So by definition, we talked about what the energy formula was. Remember that energy was V equals E over Q. Okay, so that was from an earlier slide, from an earlier formula. So now I've just rearranged it and said that the change in energy, delta E, is QV2 minus QV1. Now Q remains the same because we're talking about one particle moving one particle, and V2 is the change in voltage, or the change in electric potential. So from that formula, I can pull that Q out, common factor out the Q, and we get V2 minus V1, or point B and point A, or from moving it from point A to point B. And I can replace the voltage then with that formula from another previous slide where we said, hey, voltage is just going to be our K Q1 over R. All right, so there is the next formula I'm going to substitute in. And what we end up with, or what we develop then, is a formula that looks like this. So K Q1 over R2, that should be minus K Q2 over R1. And in the final step here, the K and the Q value is the same. Oops, sorry, that should be a 1. My mistake. Okay, because we're talking about the same particle here, just different distance. K is common. Q1 is coming out of the brackets. The Q out front, I'm going to call it Q2 because it's the charge that's creating the electric field. And that leaves us with the 1 over R2 minus 1 over R1. So there is our formula for the change in electric potential energy. So that formula deserves a red box. Now down below, if we want to deal with the change in voltage, then delta V, what we have to do, we're going to take the change in voltage now. So difference in electric potential. Okay, we're not talking about energy, we're talking about delta V down here. So this is our voltage that we're referring to. Is going to be delta V, which would be V2 minus V1, or VB. I'll switch to V2 and V1 since that's the notation I was using above. So we already know what V2 and V1 are going to look like. That is simply our KQ1 over R2 minus KQ1 over R2. And we can simplify that by taking out the KQ1, which leaves us with the 1 over R2 minus the 1 over R1. And that will calculate our change in voltage moving a particle from one location to the next. All right, so this previous formula, this formula that I'm circling right here, that calculates the voltage, or the electric potential of a particle at a given location. This formula down here allows me to calculate. This formula down here allows us to calculate the change in that voltage. So the voltage was this amount at point 1. What is the voltage now at point 2 going to be? All right, so now moving over to the right side here. I'm just going to get rid of that screen shade altogether. So let's look at the terms of plates, and that's what the key is over here. We're talking about parallel charged plates. We know from our electric field formula that electric field strength is equal to electric force divided by charge. Rearranging that equation, we get electric force can be calculated by E times Q, the field strength, multiplied by the charge of the particle. So I'm going to put that. Also important to put in a box. And again, this falls under parallel plates. So from our equation of work from grade 11 physics, it's force times displacement. So both of those are vectors. So force times displacement. Well, we can replace then work. We replace force with electric field strength multiplied by the charge multiplied by distance, and we use R when we're talking about electric fields. So the delta D got replaced with an R, and then our FE came in and took the place, or that's the EQ took the place of the force. So there is the amount of work it takes on a particular particle within two plates. So finally, if I want to know delta change in energy, delta E, so putting everything on the proper sides, I just said that EW is going to be electric field strength multiplied by a charge multiplied by the distance, and delta E is going to be the charge multiplied by V2 minus V1. Maybe I'll add the extra step in here. It comes from the left side here, that equation, but it's going to be your QV2 minus QV1 right here, sorry. Using some common factoring then. Take the Q out, and you're left with voltage 2 minus voltage 1. The Q's then would cancel out. And we can find that on the right side, V2 minus V1 is just the change in voltage, or the difference in voltage. And on the left side, we're left with electric field strength multiplied by that radius. So we have that formula, then too. It's one of the last ones that we have for our electric field theory stuff. Okay? So there we go. I've thrown a whole bunch of formulas at you, and the whole key here then is to keep them straight. So it's a good thing to transfer them to a rough cheat sheet or formula page now, clearly identify what they are. Because a lot of the word problems, you need to just decode what's given information here. So starting in some of the examples, calculate the electric potential. So electric potential is your voltage, your V. A distance of 0.4 meters. So there's my R. From a spherical charge, so I'm not going to use the word obvious, but because it's a charge, we're talking about our Q. So the information we are given, we want to find V, and we're given Q and R. So we are looking for voltage, we're looking for the electric potential, and the formula associated with that is the KQ divided by R. So K, 9 times 10 to the 9th. The charge, 6.4 times 10 to the negative 6, all divided by 0.4 meters. So the voltage then, the electric potential, is 1.44 times 10 to the 5th volts. All right. So there we are, and the appropriate therefore statement would be attached to that. Moving along. How much work? So we're looking for how much work. Work is another form of energy. So we always do it with EW, or E subscript W. So that's what known is, and maybe I'll go back to a more traditional format of writing what I know and don't know on the side. Must be done to increase the potential of a charge of, so we're given the value of the charge. Here we are. Now, increase the potential of a charge. So you're increasing the voltage, which is 120 volts. So there are 3 pieces of information. So now you return back to your formulas that we talked about in your formula sheet, do some decoding, and we move back. Just want to take a show here. We found that delta V, your change in voltage in the bottom here, is equal to electric field strength multiplied by R. That's for parallel plates. That's not the one we're looking for. We are looking for this one right here. One sec here. We are going to have to do a combination here because we know that the electric field strength multiplied by distance is delta V. So that means when we want to use our work formula, so returning to the example here, we want to find EW, and the equation that you're given from the note is electric field strength multiplied by charge multiplied by displacement. But we know that electric field strength multiplied by a charge, or sorry, by the radius, I'm going to have to rearrange that, ER multiplied by Q, is actually, from the previous formula, just the change in voltage or the increase in voltage. We're given that piece of information, 120 multiplied by your charge, 3 times 10 to the negative 7. So we find that the amount of work required to make a 120 volt change in potential is going to require 3.6 times 10 to the negative 5th joules. So you have your, again, appropriate therefore statement for that particular question. All right, in a uniform electric field, so that means that we're dealing with plates, could be Earth's electric field as well. It's a uniform field, so that means the lines are all parallel. The potential difference between 2 points, 12 centimeters apart. So we are given R. I'm converting that to meters immediately. And we are given potential difference between 2 points. So we are given delta V, voltage difference, 10 square volts. And not really given anything else. Calculate the magnitude of the electric field strength. Electric field strength is what we are looking for. So very similar to the previous formula. Remember I said that delta V is equal to ER. So that is the formula that would suit us here since it has the correct information. 1.5 times 10 squared. Looking for electric field strength, distance of 0.12. Divide both sides by 0.12. And we end up with an electric field strength of 1,250 newtons per coulomb of energy. All right. So you can see that a bit of a theme here. A lot of the questions are, I'm not going to call them perfectly straightforward, but they, it's a series of decoding the question, or a process of decoding. So electric field strength between 2 parallel plates. Electric field strength equals 450 newtons per coulomb. The plates are connected by a battery with a potential difference. Potential difference is voltage. So we have 95 volts. What is the plate separation? So we're looking for how far are these plates separated. So we're looking for that distance in there. So again, going back to your formulas, you're looking at them. We find the electric field strength is equal to delta VR. Actually, I'll just use the formula from the previous slide here. VR. So we know we have 95. We know the field strength is 450. So we are looking for R. Divide both sides by 450. And we get R equals 0.21 meters. So really the most challenging part in this process here is doing the decoding, because the actual formulas, mathematical formulas that are involved are fairly straightforward, fairly simple for you to manipulate. The difficulty comes in breaking down the terminology and matching the correct numbers with the correct terminology. That is definitely going to be the biggest challenge for this section and keeping them straight. So there is the assigned homework for this section. You know where I'm going to be tomorrow, obviously. So if you have any questions, please ask. And if you need any clarification with the homework or the note itself, please make sure you also ask for clarification. So anyhow, we'll see you tomorrow.